Hello, good evening to all. My name is Ganesh Shankar Bhandari, and I am a PMRF research scholar, PhD research scholar in IIT Roorkee, and I am here to take the NPTEL live session for the NPTEL course Principles of Extractive Metallurgy, taught by Professor Taran Kumar Kundu from IIT Kharagpur. This is live session for week 10 lectures. So, we will start with the revision of the we will first start with the revision of the previous week lectures. Then after the revision of the previous week lectures, we will go with uh, after the previous week lectures revision, we will try to solve some MCQ type problems based on the previous week lectures, which will help you further in solving the assignments for this particular course. So before this week lectures, we had talked about the extractive metallurgy of different non-ferrous metals. So in this week lectures, we will talk about the extractive metallurgy, or we can say iron extraction in the blast furnace, which is also known as reduction smelting process, or we can say carbothermal reduction smelting process. So generally, as we all know, the iron production is mainly done in the blast furnace iron making, which is a carbothermal reduction smelting process. So we will talk about the reduction when we talk about the reduction of iron oxide. So generally in the ore, it can be found in the form of either in Fe2O3 or Fe3O4, which is known as hematite and magnetite respectively, and then it can be in the form of FeO. So the reduction scenario will be like this. First, it will get converted to initially it will be in the Fe2O3 form. Then Fe2O3 via reduction process will get converted into the lower oxidation state of iron, that is Fe3O4. Then Fe3O4 will get converted to the FeO, and then from FeO it will get converted to the Fe. So talking about the oxygen percentage in these compounds, like Fe2O3 contains 30% of oxygen, something like that, and Fe3O4 contain around 28% of oxygen, while FeO oxygen get reduced to 22%, and in Fe metallic iron the oxygen will be on like 0%. So generally the reduction of oxides starts like from Fe2O3 to Fe3O4 conversion starts above 567 degrees Celsius, either using carbon CO gas or H2 gas. Whatever type of reduction gas we are using, the reduction of these oxides will start after 567 degrees Celsius. So according to the thermodynamic calculation, we can either go for carbothermal reduction, which involves direct and indirect reduction process. Like direct reduction process is the reduction carried out with the help of the carbon itself in the solid form, while indirect reduction comprises the reduction of the iron oxide into metallic iron via carbon monoxide. While we can also go for the hydrogen reduction process, which can provide higher level reaction kinetics as compared to the carbon and carbon monoxide. So coming to the iron making in blast furnace iron making, both unit processes, that is reduction of iron oxide and smelting, is happening simultaneously. So the reduction of iron oxide includes the lowering of the iron oxides to the respective metal with the help of carbon and CO generated from the coke. While in the smelting operations, so as we had already discussed in the previous week lectures, so smelting is a collaboration of two words, slag plus melting. So we are generating some slag to remove the impurities during the iron ore reduction process in blast furnace. Like this iron ore contains SiO2 and Al2O3 majorly as a gangue mineral. So we have to remove them to get high purity pig iron or molten iron. So we have to generate for removal of this SiO2 and Al2O3 gangue material, we have to form the slag inside the blast furnace. So that's why this process is known as the smelting process. And to facilitate the formation of the slag material, we have to add some flux material inside the blast furnace during the blast furnace operations, like limestone and dolomite, for the facilitation of the slag removal. So these all reactions happen simultaneously inside a single reactor during the iron making in blast furnace operations. The weighted charge or burden generally consists of iron ore lump, sinter, pellets, which can have a size of around 10 to 20 mm, while coke has to be charged having a size range of around 50 mm. Then we also have to charge the limestone and dolomite material having a size range of around 25 to 30 mm, and this is done with the uh, charge done with the modern bell type system with proper gas sealing, so exhaust gases cannot get out from the blast furnace during the charging operations. So during burden descent, heat and mass exchange with the hot gases comprise CO, CO2 and N2, which are moving up. Thus blast furnace is a very efficient counter current heat and mass exchange reactor, because height of the blast furnace is around 25 to 30 mm and the diameter can be up to 100 mm. When talking about the preheated, uh, so preheated humidified O2 enriched air blast, we provide generally in the blast furnace at a pressure of around 2 to 3 atmospheric pressure, which is provided with the help of the tubers, which can be 12 to 18 in number. Then uniformly through the periphery just above the hearth region of the blast furnace. Incomplete combustion of carbon with hot air blast generate heat and CO in front of the tubers, which can increase the temperature up to around 1960 degrees Celsius. So we are charging three different things inside the blast furnace. One is the iron ore material, which can be in the form of lump, sinter, ores, or pellets. Then we are charging the coke material, and we are at the same time we are also charging the limestone and dolomite material. So coming to this hearth region, or we can say this. This blast furnace contains this Bose uh, different regions like stock line, stack, Bose region, then there is hearth region. So the temperature of these regions varies as we are going downward. So the temperature will get increased inside the blast furnace. So during this Bose region, the coke will be the only material which will remain in the solid form. Either when we are talking about iron oxides and the dolomite and limestone material, that will get uh, converted into the liquid material. Only the coke will be in the solid form. So due to this coke which is in the solid forms, and at the same time this coke is getting coming in the contact with the hot air blast which we are providing from the tubes in the form of the oxygen gas. So this oxygen gas will react with the carbon material at the Bose region, and due to the reaction between the carbon and oxygen, and exothermic reaction will happen, and it will increase the temperature at around the tubes at up to around 1960 degrees Celsius. So the reduction of, as we had already talked about in the blast furnace, we can observe two types of reduction of iron oxide. One is direct reduction, and then second one is indirect reduction. So direct reduction occurs with the help of the coke itself. So that will be like solid to solid state reduction. Then coming to the indirect reduction, that happens with the help of the carbon monoxide generated during the process, and that is indirect reduction, or we can say gas to solid reduction. Then this is a typical diagram of blast furnace. Then coming to the partition of impurities, so amount of impurities present in the iron ore are like manganese, silicon, phosphorus, and sulfur, which are entering into the pig iron, and these are controlled by the adjusting the basicity of the slag and temperature. So P2O5, we can get it carbothermally reduced with the help of like P2O5 plus 5 carbon changing into 2 phosphorus gas and 5 CO2 gas. So this phosphorus element will get uh, it is getting converted into the metallic part. So it will get report into the pig iron. On the same time, Mn manganese metal and some amount of silicon metal will also go into the metallic part. However, if we are going to change the basicity of the slag, so we can control the amount of reporting these phosphorus, manganese, and silicon. Either they will, we can control that either they will report to the slag material or either they will report to the molten metal. Then coming to the recent trends in iron making, so in previous 60-70 years we are doing continuous research on iron making in blast furnace to improve the efficiency of the blast furnace reactor. uh, so reduction of iron ore in the blast furnace require high grade metallurgical coke, which is very costly. And India, when we are talking about India, so we have limited access for the coke, metallurgical coke grade coal, which can be converted into the metallurgical coke. So we are importing the coke grade coal material from other countries, and it is very costly. So, which is metallurgical grade coke is very costly and polluting production method from not so abundant coking coal. Thus, step like preheated blast, oxygen enrichment in the blast, injection of hydrocarbon, pulverized coal, and steam into the blast has been incorporated during these times, so that we can increase the efficiency of the blast furnace without adding more and more coke material inside the blast furnace as a fuel source. Then in oxygen enrichment, gas volume decreases and the amount of heat transferred from the extending gas to the charge. So previously, if we talk about 70-80 years ago, we were purging directly air inside the blast furnace as a preheated gas. Now we are trying to enrich the oxygen inside that preheated blast furnace gas, which we are providing to the tuers region. So what will happen as we are increasing the amount of more and more oxygen inside this preheated air? So the reaction kinetics will become faster. On the other hand, we are decreasing the amount of nitrogen inside the blast furnace. So the flue gases which are coming outside from the blast furnace, the amount of those flue gases will become lower. Then increase in top pressure of the blast furnace gas reduces the pressure difference between the gas and at the stack and at the tuer level, which decreases ascending gas velocity, thus gets more contact or residence time with the ore lump and hence reduces the coke rate and increases the rate of production of pig iron. So the major focus is on the increasing how to increase the efficiency of the blast furnace, at the same time how to decrease the coke rate inside the blast furnace during the blast furnace iron making process, because we need if for example if we talk about 70-80 years ago, we were charging around 750 to 800 kg of coke for per ton of pig iron production. Nowadays, it has decreased up to around 450 or 500 kg per ton kg coke per ton of pig iron production during the blast furnace iron making process, by with the help of these improvements like oxygen enrichment, preheated air, then oxygen injection of hydrocarbons, pulverized coal injection to through the tuers region. So they have modified the process in order to decrease the coke rate inside the blast furnace. Then combustion of the injected hydrocarbon into the stack of the furnace generate two reducing gases. So if we are going to inject the hydrocarbon inside the furnace, so majorly we are introducing CH4 as a hydrocarbon material. So CH4, after uh, getting combustion with the oxygen, it will provide two different reduction gases. One is CO and another is hydrogen. And that will improve the indirect reduction process of the iron ore in the blast furnace making. And as we can see, this is a gas solid type reaction. So the reaction kinetics will get improved. So CO and H2 together improve the efficiency of the indirect reduction, as they are better reducing agents above and below 800 degrees Celsius respectively. Since combustion of coke is much more exothermic than that of hydrocarbon, a higher increase in blast temperature is required for hydrocarbon injection in order to maintain the hearth temperature. So there are some disadvantages also. So we cannot go for very high hydrocarbon injection. We have to optimize that hydrocarbon injection, because in order to inject the hydrocarbon inside the furnace, at the same times we also have to increase the blast furnace temperature as the at the hearth region or tuer region. So steam injection through the tuer generates CO and H2 but decreases the hearth temperature due to highly endothermic reaction, like H2O plus C getting converted into H2 plus CO. This necessitates high blast preheat and or oxygen enrichment to achieve the required hearth temperature. So how we can increase that particular temperature inside the blast furnace? Either we have to provide more and more coke, but the main problem is this, main problem is there, we are trying to inject this hydrocarbon inside the blast furnace so that we can decrease the coke rate inside the blast furnace. However, we need to increase the temperature at the tuer region. So in order to maintain that particular temperature for this endothermic reaction to get happen, we need to provide more and more preheated gas inside the blast furnace so that we can control the temperature at that particular region for this highly endothermic reaction to get happen and to increase the indirect reduction processing inside the blast furnace. Although blast furnaces have very high capacity and production rate, they suffer from disadvantages like poor control over composition variation of the pig iron from tap to tap, high capital and operating cost, then requirement of very costly coke as reductant. So there are some disadvantages like we cannot precisely control the pig iron composition coming out from the blast furnace, because that involves numerous factors, like we have to achieve a desired slag content, and in order to achieve this desired pig iron content, we also have to control the ore which we are providing inside the blast furnace as a feed material. On the other hand, a blast furnace can making of blast furnace can cost up to around 150 to 200 crores. So very high capital investment is there, while alternative iron making processes we can develop a plant in just 5 or 10 crores, 5 or 10 crores. So very high capital and operating cost is there. Then the requirement of very costly coke as reductant. There is no alternative for the coke as a reductant inside the blast furnace that we have to provide. So, okay, then, yeah. Now, we had talked about the blast furnace iron making process, and we had talked about the major disadvantages for the blast furnace iron making process. So, when what if we don't have that much capital cost to get to invest for the iron making process? So there are some alternative routes of iron making which are known as direct reduction, which are generally known as direct reduction processes. So they can incorporate other coal materials also, which we cannot get converted into the coke material. So there is no such requirement. They are not running on the coke material only. They can incorporate different types of fuel material or different types of reductant inside the processes. So the limitations and disadvantages led to the development of two important alternatives to the blast furnace, namely one is direct reduction and second one is direct smelting reduction processes. So direct reduction is DR, then direct smelting reduction is DSR processes. So DR processes produce solid iron with very little indirect reduction reaction in the form of direct reduced iron. So that is known as DRI, or we can say sponge iron, which produced via direct reduction process. So in this type of reduction processes, the reduction is happening in the solid state only. We are not going for the liquefaction of the material. We are doing the reduction in the solid state itself. Then this solid sponge iron can get we can use this solid DRI as a feed material in the electric arc furnace and other steel making processes like hearth furnace or basic oxygen furnaces. We can use this DRI. Then and DSR, while the DSR process produces hot metal without using high grade coke material, We can use the coal material, we can use hydrogen gas as a reductant, we can use carbon monoxide gas as a reductant. So there are numerous number of processes which we can use e- uh, we can use for the alternative iron making process. The DR processes use rotary kiln, low shaft furnaces, static bed reactors, and fluidized bed furnaces. The rotary kiln uses solid reducing agent, coke, breeze, coal dust, char, or anthracite. So we can use different types of coal material inside the DR during the DRI process, whereas other units use a CO plus H2 mixture for reduction of iron ore pellets or fines. So in other processes, we have to use. So there are different types of processes for direct reduction iron also. So if we are talking about the rotary kiln process, so we can go with the different types of solid reducing agent. While if we are going for the direct reduction DRI production in low shaft furnace, static bed reactor or fluidized bed reactor, in that case we have to use gas as a reductant material in the form of carbon monoxide or hydrogen oxide. Hydrogen. Then the fluidized bed furnace is operated at 750 degrees Celsius due to efficient heat transfer and better reducibility of hydrogen below 800 degrees Celsius. So in the blast furnace during the blast furnace making, we were operating at a temperature of around 1800 or 1900 degrees Celsius. While in the fluidized bed reactor, or we can say direct reduced iron facilities, we can operate as much as lower temperature up to 750 or 800 degrees Celsius around. While in the DRI process, we have to operate it at around 1000 to 1200 degrees Celsius. We can operate. Then alternative. Then coming to the direct smelting reduction process, the DSR processes permits use of non-coking coal as reducing agent. So when we were talking about blast furnace iron making, we only require coke as a reductant material. While in the DSR process, we can use non-coking coal also as a reducing agent. So we don't have to convert the coal into the coke. We can directly use the non-coking coal material as a reducing agent and require lesser ore preparation, like only pelletizing or sintering can be uh, is required, and materials handling consumes lesser energy, provide better pollution control, and work at lower operating cost. Apart from these advantages, DSR processes can be installed at low capital cost and made continuous for iron and steel production, like pig iron from the blast furnace, which can be fed directly to the steel making units in further operations. And these advantages have led to the development of a large number of DSR processes throughout the world. The Osmelt submerged lance technology have a promising future in direct smelting reduction of iron ores. So both the gas-based DR and DSR process are formed natural gas by steam oxygen. So we can use the natural gases also as a reductant material. Uh, the water gas reaction is enhanced by the suitable catalyst nickel platinum at around 700 degrees Celsius. So we can produce CO and H2O by reforming of natural gas. The proportion of CO, H2, CO and H2O around contains around 40% carbon monoxide, 45% hydrogen and 12% CO2, 3% CO. In reform gas mixture is adjusted by the temperature control. So coming to the classification of direct reduction processes, so we are talking we have iron ore sources like pellets or lump or we can say having bigger size than 10 mm. Then on the other hand, we are having some fine ores like size lower than 1 mm. So for pellets or lump ore, we can go with the shaft furnace processes, while for fine ore, we can go with the fluidized bed reactor or rotary hearth or rotary kiln type processes. While the pellets or lump ore also can be introduced inside the rotary hearth or rotary kiln processes, generally in the rotary kiln processes mainly. Then shaft furnace includes direct reduction processes like Midrex or HYLI energy on or Corex or direct reduction process, while fluidized bed reactor includes Finmat or iron carbide process or Circofer process. Then rotary heart include Comet, Fastmat. So these are different processes which are developed by the different companies worldwide for the production of the iron via alternative iron making routes. Okay. Then coming to the direct smelting reduction process, so pellets, it is like similar to the previous one. Then coming to the important sponge iron making processes which are widely used worldwide. First one is rotary kiln process. So in India, around we can say 30 to 40% of iron production is done with the help of the rotary kiln processes only. Most of the uh, minor companies are producing the iron ore with the help of this rotary kiln process by producing direct reduced iron, or we can say sponge iron, because blast furnace we can see only a few major players in the industry have the blast furnace operations like SAIL or Tata Steel, or Jindal Steels. Otherwise, most of the minor companies present in this field are using the direct reduction processes like rotary kiln process for the production of the direct reduced iron. So rotary kiln processes are coal-based processes using sized iron ore lumps and a relatively coarse fraction of non-coking coal. The coal-based rotary kiln is more popular in India due to limited availability of natural gas. So we preferred more like coal-based rotary kiln processes because we have abundance of coal material that we can use as a fuel source inside these rotary kiln processes. Then coming to rotary process, which is also known as fast mat process, are coal-based processes in rotary hearth furnaces to treat waste like flue dust from blast furnaces, mill scales, and ore fines in the form of briquettes and pellets. So then coming to the fluidized bed process, which is also known as FINMAT process, is for continuous reduction of iron ore fines by reformed natural gas in a train of fluidized bed reactors. So in the above two processes, we were majorly using the fuel source in the solid form, which was non-coking coal, while in fluidized bed processes, we are using reformed natural gas. Uh, for the reduction and fuel. Then coming to vertical low shaft furnace, the major example is Midrex process, which is developed by the Midland Ross Corporation, Cleveland, USA. Uh, this process is continuous counter current moving bed process similar to the bottom two-thirds of the blast furnace. Ore lump and pellets are charged from the top, whereas preheated reformed natural gas is blown in the lower part of the shaft. So mid-rack process is predominantly followed by HYL third and HYL IBM energy on reforming of natural gas, reduction of iron ore, and carbonization of DRI proceeds simultaneously in a single reactor. So in some iron making alternative iron making processes, we are using coal as a fuel and reductant material, while in some other processes, we are using natural reformed natural gas as a fuel source and reductant. So important commercial direct smelting. Now coming to the direct smelting reduction processes. So there are some processes like Corex process, which is based on the pre-reduction in a shaft furnace and melting in Mettler gasifier, which is developed by Korf Stel Germany company, is the first commercial direct smelting reduction process. Which was developed around 20-30 years ago. Then coming to the smelt process, a wide variety of coals like -6 mm and iron oxide having size of -6 mm of different quality and steel plant waste along with fluxes are inducted to specially designed lances into a carbon saturated molten bath, and the process can accept 100% of fines also. Then coming to the FINEX process, here the pre-reduction step is similar to the FINMAT DRI process where ore fines are reduced in a series of fluidized bed reactor, and the melting step is similar to the Corex in a melter gasifier. While the fast melt process is based on pre-reduction of intimately mixed iron ore fines and solid reductant in rotary hearth furnaces and melting of DRI electric iron making furnaces. The IT Mark III process produces pure iron nuggets by charging green composite pellets of iron ore fines and pulverized coal in rotary hearth furnace heated to around 1350 to 1500 degrees Celsius for clean separation of iron from liquid slag. The nuggets are used in electric arc furnace or blast basic oxygen furnace for the further steel making process. Okay, so that was all regarding the iron ore iron ore production. So we can go with the we can go for iron reduction processes via either via blast furnace operations, which require metallurgical grade coke and having very high capital cost and operational cost. While the more we have some disadvantage, and to fulfill those gaps, we are researchers have developed some secondary iron making processes also, which requires lower capital cost, and they do not require metallurgical grade coke, which is very costly. And we can go for direct reduction process by using secondary operations, or we can go for direct smelting reduction process with the help of the different processes uh, developed by researchers through, all over the world. Now we will talk about halide metallurgy, or with the help of halide metallurgy, we will talk about the how to extract titanium, zirconium, hafnium, uranium, and silicon purification. So halide metallurgy, as the name suggests, it includes the metallurgy with the help of the chlorine, fluorine, bromine type compounds, and with the help of these compounds we are trying to extract the material. We are trying to reduce the other compounds in order to extract the pure metal, pure metallic composition. Then halide metals, metal halides that are normally formed with a smaller negative free energy change. Then their oxides can be utilized to extract those metals, like titanium, zirconium, beryllium, aluminium, uranium, and magnesium can be extracted with the help of the halide metallurgy. So most metal halides are volatile or having very low decomposition temperature, so that they can be this makes it possible to separate certain metal halides and purification by the distillation process. So we can reuse these metal halides again and again with the help of this property. Halides form highly melts with lower melting points than oxides. So this particular property helps in the production of the aluminium from the bauxite ore. When we are talking about the bauxite ore, so bauxite ore is having a melting temperature of around 2300 or 2400 degrees Celsius, and very high carbothermal reduction temp. At the same time, having very high carbothermal reduction temperature also, which is infeasible, which is commercially infeasible to extract the aluminium from their particular oxide. So with the help of this conducting melt salts, we can go for the production of aluminium from the with the help of this halide metallurgy. The common example is Hall Herold process, which uses sodium fluoride salts as a electrolyte, and that electrolyte lowers the melting point of the Al2O3 inside the system, and at the same time we are using the carbon for reduction of the Al2O3 to get it converted into the aluminium metal. So thus metal halides may be used as molten salt electrolytes in the electrolytic extraction of aluminium, magnesium, and sodium. As carbon tetrachloride is less stable than most metal chlorides, carbon cannot be used as a reducing agent for the metal chlorides. So HCl becomes more stable as the temperature gets increases. Therefore, H2 can be used as a reducing agent for several metal chlorides at high temperatures. And more stable metal halides of uranium, titanium, beryllium, zirconium can be reduced by a metallothermic reduction using aluminium, magnesium, calcium, or Na as the reducing agent. For example, UF4, uranium fluoride, getting reacted with magnesium can get converted into uranium metal, and at the same time producing magnesium fluoride as a byproduct. The heat and it is very highly exothermic reaction, so the heat produced is sufficient to fuse both products along separation of MgF2 into an appropriate slag material. Certain metals like iron, niobium, and aluminium from several chlorides, the higher chlorides are easily reduced with hydrogen to lower chlorides, while various disproportionate reactions may occur at certain temperature, allowing some interesting separations. Like AlCl3, with the help of the aluminium liquid at around 1000 degrees Celsius, can get converted into AlCl gas. While with the help of cooling, we can produce aluminum solid and AlCl3 gas. So coming to the next, anhydrous metal halides preparation. So halogens of oxides is the most common halogenation of oxide is the most common method for preparing metal halides, in which metal stable oxides of rare or reactive metals are mixed with suitable reducing agent like carbon, hydrogen, sulfur to remove oxygen and charged to the top of a shaft furnace. So halogens is introduced at the bottom and the heat required to start the reaction is supplied electrically in a coke bed. The reaction are normally exothermic and may be sufficient to maintain the process autogeneously between 500 to 700 degrees Celsius. So magnesium oxide reacting with the calcium, reacting with the chloride and carbon can get converted into MgCl2 and CO2. And this MgCl2 can be further used in the halide metallurgical operations. Halogenation of ferroalloys or carbides with chlorine can be conducted without the need of a reducing agent and without the danger of producing oxyhalides. Then crystallization of alkali metal halides will hydrolyze from the aqueous solution obtained by leaching with an appropriate acid, for example HCl. The main disadvantage of using halides are like many halides except alkali metal halides are really hard, readily hydrolyzed. Like MeCl2 plus H2O can get converted into metal oxide and producing the HCl as a byproduct and must therefore be stored in dry places. Fluorides are generally less susceptible to this problem but tend to be more expensive. So we can, when we talk about the halide metallurgy, so we generally prefer metal chlorides as a reducing agent or reaction to get happen. Although fluorides are more stable as compared to the chloride materials, but the cost is a bigger factor for choosing metal chlorides as a reducing agent. Then halogens cause considerable corrosion problems in the processing plants, and corrosion is a major problem because during the process it can produce Cl2 gas or it can produce HCl gas as a byproduct, so that will create a major corrosion problem inside the processing plant. When halogens are costly reagents and not easily no cannot be easily regenerated. So coming to the production of titanium by Kroll's process. So rutile having around 90 to 99% TiO2 is get mixed with the coke to make briquettes. Then chloride gas is parts in the fluidized bed reactor to convert this TiO2 into TiCl4, and then TiCl4 get condensed at around 200 degrees Celsius to remove the gas produced during the TiCl4. So this TiCl4 is getting converted into the gaseous material, and at condensation at around 200 degrees Celsius will lead to the removal of FeCl3 present as a impurity material inside this TiCl4, and then we are getting TiCl4 liquid via scrubbing operations, and after this we are reducing it with the help of the H2S to reduce VOCl3 to get them converted into VCl3, and after that fractional distillation can provide us pure TiCl4, and then this TiCl4 which we have converted uh, the titanium oxide which we have get converted into the TiCl4 for via halide metallurgy. This TiCl4 is subjected to the magnesiothermic reduction with the help of the magnesium in the with the help of magnesium in the Kroll's process, and with the help of vacuum distillation we can produce Ti alloy ingots. Okay, yeah. So Kroll process and magnesium as reductant. Kroll consider magnesium as a reducing agent due to relatively low melting point around 74 degrees Celsius. So of MgCl2 and high boiling point of Mg. This thing we have to kept in mind during the processing itself. This Mg we are providing the Mg material for the magnesiothermic reduction, and this magnesium is getting converted into the MgCl2, and these two things have a major difference in their melting and boiling points, so that we can separate out this MgCl2 material at their boiling point to recirculate it back into the Crolles process. Although magnesium is having higher cost as compared to the Na, so why we can't sodium inside the sodium as a reductant material during the Crolles process? Because sodium is having very narrow range of working temperature, which is only 80 degrees Celsius. Like sodium metal is having a melting point of so sodium metal is having a boiling point of around 8 melting point of around 882 degrees Celsius, and NaCl is having a melting point of around 801 degrees Celsius. So the difference between these two is very lower on very lower side, so we cannot go for the sodium as a reductant during the Crolles process. While in Hunter process, the slag NaCl cannot be removed by vacuum distillation, and leaching leads to the oxidation of the titanium sponge. Sodium is more costly, reactive, and hazardous compared to the magnesium. Temperature control is very difficult as the reduction reaction is highly exothermic. So it is not used for the production of the titanium through further research work. Although further research works are going on titanium, because sodium is having abundance high sodium metal is sodium chloride is having high abundance as compared to the magnesium chloride. So the commercial use of Ca as a reducing agent has been discouraged due to its higher cost, scarcity, narrow working temperature range, and difficulty in CaCl2 removal during the process. The Kroll reduction reaction is also highly exothermic, resulting in a portion of the titanium metal adhering to the container's inner wall. The eutectic point for a titanium Fe binary alloy is around 1085 degrees Celsius. Thus, a liquid phase of titanium Fe alloy forms at around at temperatures above 1085 degrees Celsius, which can lead to the rapid alloying of titanium and the steel, and that can cause harm to the reactor itself, which can damage to the container. Thus, the Crolles process require strict control of the reduction temperature. Like we cannot go beyond the 108, we cannot go above 1085 degrees Celsius to inhibit the formation of this titanium iron alloy, so the container does not get damaged. Then coming to the zirconium and hafnium production, so hafnium extraction. So zirconium, or we can say zircon sand, uh, is having formula of ZrHFSiO4. So with the help of the fluidized bed reactor, by passing Cl2 gas, we are getting them converted into ZrCl2 and HFCl2 while producing CO2 and SiCl4 as a byproduct. And with the help of solvent extraction, we can extract out we can separate them out into ZrCl2 and HFCl4. So from the ZrCl4, with the help of solvent extraction, we can get out HFO2 and ZrO2 we can create. Then by a secondary carbochlorination process, we can again convert them into ZrCl4, and with the sublimation or distillation process, we can produce ZrCl4. Then with the help of magnesiothermic reduction, we can produce zinc zirconium sponge, and with the help of vacuum distillation, we can extract out this MgCl2 and Mg from this zirconium sponge, and we can produce zirconium sponge, and by a crushing and vacuum arc melting, we can produce zirconium and zirconium alloy ingot. While for the HFCl4 production, we can go with only chloride distillation process or extractive distillation process to remove the HFCl4 from the system, and ZrCl4 produce can be further processed for the production of the zirconium metal and alloy. While this HFCl4 again HFCl4 produced during the process can uh, we can go with a similar process as we were going in a zirconium extraction, like we can go for magnesiothermic reduction process, and or we can go with the molten salt electrolysis process, followed by vacuum distillation and leaching respectively, to produce HF sponge and HF crystal, and via refining and melting process we can produce hafnium alloy ingot. So HF has a large neutron capture cross section 550 times that of ZR. Thus, when ZR is used for fuel rods of nuclear reactor, HF should be less than 50 ppm. ZR is produced through solvent extraction or chloride distillation process. Now coming to the silicon extraction process. So metallurgical grade silicon is having a purity of around 98%. However, the major uh, value of the silicon is in the form of the semiconductor material, which is used in the solar panels, and it requires 99.9999, or we can say 6, at least 6 N purity, 6 9 purity, to be used in the to be used as a semiconductor material. So metallurgical grade silicon can be produced with the help of the carbothermal reduction process, like SiO2 solid plus 2 carbon at high temperature can get converted into silicon liquid, plus CO2 is going into the gaseous phase. So and as we have already discussed, the major value of the silicon production is lying in the production of the semiconductor silicon material, which requires at least 6 9 purities to be used in the semiconductor material. So for production of this industrial polysilicon production, we use Siemens process for the production of the 6 9 purity silicon material. So silicon in the solid form, with the help of the halide metallurgy, like we are trying to convert this into the chloride compound. So Si plus 3 HCl in the gaseous form can get converted into SiHCl3 plus H2 gases. The reaction is highly exothermic and heat removal is essential to assure maximum yield of trichlorosilane. Various impurities such as Fe, and boron are removed by forming their halides like FeCl3, AlCl3, and uh, these are obviously at high temperature are in the gaseous form, so they can be distillated with the help of the distillation plants. Now coming to the uranium production, so from the mining, whatever the uranium ore is coming, it is having just ppm level of uranium inside that particular ore. So then after mining and milling and beneficiation, we can milling, beneficiation and different mineral processing itself, we can produce a yellow cake which is having uranium oxide, or having formula U3O8. So this uranium oxide or yellow cake generally contains not more than 4 to 5% of uranium inside that yellow cake. After that, this has to be treated in the metallurgical operations via conversion process to get them converted into uranium hexafluoride UF6, and via enrichment process we can get low enriched uranium, and with the fuel, and after further refining we can convert them into the fuel. So UF6 pumped into fast spinning 90,000 rpm cylinders centrifuges, where heavier isotopes, uranium 238, are pushed towards the walls of the cylinder, and the lighter uranium 235 stays in the center of the cylinder. Finally, enriched UF6 is converted to uranium dioxide powder, which is manufactured into fuel rods for use in the nuclear power plant reactors. Now, purification of bulk metals or chemical refining. So, when we are trying to produce the